Okay, our learning goal for this video is I'll be able to graphically represent vectors. I'll be able to convert between polar and Cartesian form of vectors, and I'll be able to find the unit vector of a vector. So starting with graphically representing vectors. Position vectors in the plane. As a vector has both magnitude and direction, it can be represented in two-dimensional planes. In the figure at the right, the vector u joins the point from A to B. An identical vector can be considered to join the origin with the point C. So looking at this top right image compared to the image below it, we can see we've taken that point A to B, and we've moved it so that it's a new point from the origin to the point C. It's easy to see in this second image that u is made up of two components, one along the x-axis and one parallel to the y-axis. Let I be a vector along the x-axis with magnitude of 1, and let j be a vector along the y-axis with magnitude of 1. These vectors are known as the unit vectors. These can also be written as just I and j with the squiggly line, the tilde, I should say, underneath it. The position vector u is made up of some multiple of i's in the x direction and some multiples of j in the y direction. So up at this image here, we can see we can fit one more I in there and then maybe half of an I. So if we were to write this in its form, we might find that that's 2.5 lots of I and then 2 lots of j in that direction. So we can see we can start using portions of these unit vectors to describe u in terms of how far does it go in the x direction and how far does it go in the y direction. And we see that here in the next image. For example, if the point C has coordinates 6, 3, then u is going to be 6i plus 3j. So 6 lots of the I unit vector and 3 lots of the j unit vector. The Cartesian form of a vector from the origin to the point xy is given by xi plus yj. If we have it in xi plus yj form, we can express it instead as an ordered pair, bracket xy, close bracket, or in a column vector, which would stack the two on top of each other. Using Pythagoras' theorem, we can find the length or magnitude of a position vector. Denoted as u with two absolute value signs around it, or the other way we can refer to it is r. So if you imagine u as a circle of all possible vectors with the same magnitude, we can see that that magnitude would be the radius of this circle, right? So consider the vector 6i plus 3j. U is going to be the square root of the x component squared. Well, it doesn't matter what order you do because addition is commutative, but let's say the y component squared plus the x component squared, which in this case is going to give us square root of 45, which is the same as 3 root 5, because we can take out that factor of 9. The magnitude of a vector u equals xi plus yj is given by, so this is our general form, the square root of x squared plus y squared. Some things to note about our magnitude: it's always going to be positive because it's going to be the sum of two square values, and then when you square root it, yes, it could have a positive or negative answer, but because we're looking at a sort of length of our line, we can't have negative length, so we just consider the positive solution to this square root. The other piece of information we can get from this is the angle, so the angle it makes with the x-axis. Right? Now, in terms of the angle it makes with the x-axis, we consider it two ways. It can either be the positive direction from the x-axis or the negative direction from the x-axis. Either is acceptable in polar form. In this case, we're going up and to the left, so we know our value for theta in this case would be positive. So using trigonometry, the angle theta can be represented as theta is equal to the inverse tan of y over x. Now, where does this come from? It just comes from trigonometry. If this is our angle, our opposite is 3. and our adjacent is 6. So opposite over adjacent is going to be the y component over the x component. So in our case here, we'd have tan inverse of 3 on 6, which is equal to, I believe, 22. Let me check. 26.6 degrees. Okay, so the vector in polar form is u is equal to, we use square brackets for this. Make sure you're always using square brackets, not curved brackets, r comma theta, and then we close the square brackets. So in this case, that would be 3 root 5, 26.6 degrees. And I see down here I jumped the gun a bit because we're now looking at the general form. So the general form is r comma theta, where r is the magnitude, and in the direction of theta equal to tan inverse y on x from the positive direction of the x-axis. So let's take a look at an example. Using the vector shown, determine the magnitude of u, the direction of u, express the angle with respect to the positive x-axis. They then want to find the true bearing of u and the expression of u in polar form. So we have this first angle we can look at, which is the angle it makes with the positive x-axis, and then the second angle that I'm going to do in orange will be our second angle coming through from a true bearing. So something to note about this vector is that we have negative y direction and positive x direction. That places us in the fourth quadrant, which means our angle is going to be between 0 and negative 90, or 270 and 360 degrees. I'm going to go with the negative angle just because I think it's a little bit easier for this particular example. So part A, magnitude of u. As we talked about before, because magnitude is a distance, we're going to have only positive solutions. So we square our 3, we square our negative 5, which is going to give us positive 25. Either way, this is going to be the square root of 34, which we can write as 5.831 to 3 decimal places. So that's our magnitude of u. We have no units here, so we don't need to write our units for our magnitude. Part B, the direction of u, express the angle with respect to the positive x-axis. So our first quadrant solution to this would be if the vector was coming up here. So that would be sort of our theta 1. And what we can do is we find theta 1 just using tan inverse of 5 on 3. So we omit the negative sign, compute it based off what it would be like in the first quadrant, and then all we have to do is reflect this over the x-axis. You'll be doing more of this stuff in methods later this year, but just need to know a basic level of sort of our cast diagram and how to compute negative angles and all that. So the positive angle, the first quadrant solution, is going to be 59 degrees, which means our actual theta is going to be negative 59 degrees. It's coming down by the same distance, but it's just going in the opposite direction. So that's our angle with respect to the positive x-axis. If we were to take it from true, so this is the orange angle here, that is going to be 90 degrees plus theta. So 90 degrees plus 59 degrees is going to equal 149 degrees true. Okay, and part D, express u in polar form. Well, u is equal to square brackets of r, which in this case is 5.831, and negative 59 degrees, or the other way you could write it is negative 34, negative 59 degrees. So this is what I was talking about earlier. Note before, do not use theta equals tan inverse of negative 5 on 3. This will give the same answer as theta equals tan inverse of 5 on negative 3, which the calculator calculates as. I'm going to leave that as an activity for you. Plug that into your calculator, see how it's different and why it can't be the solution that we're looking at. So if we do this whole first quadrant, fourth quadrant method, that saves us the trouble of having to worry about what our calculator is going to spit out for us. All right, unit vectors. As we've seen, any vector is composed of x and y components denoted by I and j. These vectors are called unit vectors, as they each have a magnitude of 1. This allows us to resolve a vector into its components. If a two-dimensional vector makes an angle theta with the positive x-axis and has a magnitude of r, then we can find its x and y components. So its x component is going to be its magnitude times by cosine theta, and its y component is going to be its magnitude times by sine theta. And this just comes from our trigonometry. So if we have a vector here with an angle of theta, to find our opposite using SOHCAHTOA, our hypotenuse is r. So if I wanted to find this y component, that's our opposite. So opposite is equal to our hypotenuse times sine. That's what we've got over here. And similar story for our x direction. It's going to be our hypotenuse, which is r, times by cosine of theta. So we can see where that comes from. So consider the vector u, whose magnitude is 30 and whose bearing from north is 310 degrees. Determine its x and y components and write u in terms of I and j, that is Cartesian form. So if we were to split this into a triangle with its y component and its x component, we notice that x is going to the left. So already we know that our final solution for x should be negative. And our final solution for y is going up, it should be positive. So what we can do is look at the triangle that this would make. What would this theta be? Well, it's going to be 270 minus 310. So that's going to be 40 degrees right there. So x is going to be negative r cosine theta. Y is going to be positive r sine theta. And in this case, our r is 30 and our theta is 40. So that is going to give us negative 22.98. And y is going to give us 30 sine 40, which is 19.28. So u in Cartesian form is going to be negative 22.98 I plus 19.28 j. If you're following along with your textbook, you'll notice that they use instead positive 30 cosine of 140 and positive 30 sine of 140. So I want you to have a think, where does this 140 come from? Plug it into your calculator, do you get the same solution? Example 8. A bushwalker walks 16 kilometers in the direction of bearing 50 degrees and then walks 12 kilometers in a direction of bearing 210 degrees. Determine the resulting position of the hiker given magnitude and direction from the starting point. State the resultant vector in polar form. So we need a diagram for this. So if we're looking over here, let's make this our positive y-axis. And this, our positive x-axis. We start with the direction true of 50 degrees. So if I'm starting at this 90 and I go 50 degrees to the right, that's going to take me to 40 on my ruler. And so we have this vector coming out here that has magnitude of 16 kilometers and a true bearing of 50 degrees, which means the angle that we actually care about is 40 degrees. Okay, and once it gets to the end of this 16 kilometer walk, we then walk 12 kilometers in a direction of 210. So if you can imagine, this is our starting point. We go around 180 degrees, and then we need to go another 30 to the left. So that's going to get us to 60 to the left on my ruler here. And let's do this in orange. That's coming down 12 kilometers. And the angle that we care about is the angle that it makes with this positive x-axis. So in this case, that's going to be coming down towards the negative. That's going to be 210 take 90, because it's not coming from north anymore. So 210 take 90. This is going to give us negative 120. Okay, and our resultant vector, which I'll draw in purple, is going to be the vector that takes us from the origin to this point here. Okay, so how do we find that vector, that purple vector? Well, what we first have to do is convert our two vectors into Cartesian form. Once we have them in Cartesian form, we can just add the components, and that'll find us our resultant. So let's call this first vector A and the second vector B. A is going to be given by 16 cosine 40 plus 16 sine 40. Can't forget my unit vectors though, I and j. That gives us 257 I plus 10.285j. 10.285j. Okay, and then B is going to be 12 cosine negative 120 plus 12 sine negative 120, which actually is the same as cosine of 240 and sine of 240, if you would prefer to strictly use the positive directions. But either way, that's going to give us 6.25... No, sorry, that's going to be negative 6. And we know it's going downwards. So that's going to be minus 10.392 J. 392. Okay, so A plus B, if we were to add its components, is going to be 12.257 minus 6, which is going to be 6.257 I. And then we've got 10.285 minus 10.392, which actually gives us negative 77. Okay, so if we were looking at this vector and comparing it to our purple drawing, we can see that it does indeed make sense. It's going approximately 6 units to the right and approximately 0.1 of a unit down. So we can check our answer there. That's really handy to do little things like that in an exam. Just take a quick look at your original diagram. Does it make sense given the context? If not, go back through and check your workings, check your calculations. Awesome. But we're not done here. We need to state the resultant vector in polar form. So we need to find the magnitude and direction of this sum that we've just done. Let's start with the magnitude. So the square root of 6.257 squared plus negative 0.107 squared gives us... Actually, I'll just jump straight to the solution. That gives us 6.26. So we can see it's only a little bit bigger than its x component, which makes sense because the y component is so small. All right, the other thing that we need to find is the angle, but first of all, let's not forget our units. This is in kilometers. Because it's a magnitude, it's a distance of the resultant vector. So our theta is going to come from tan inverse of our x over our y. We can see we're in the fourth quadrant again, so let's first consider it in terms of the second quadrant, which is going to be 0.107 over 6.257. Okay, this is going to give us the positive angle. So what would happen if this vector was actually coming up looking like this? I'll just draw it real quick. So we can see there in the nice sparkly color over there. If this purple vector was instead in the first quadrant, it'd be coming up like that, and the angle that that would make with the x-axis would be positive 0.986 degrees. But because it's in quadrant 4, it's going to be going downwards. So our theta is actually, so if we call this theta 1, our actual theta is negative 0.986 degrees. This is our quadrant 1 solution, but this is our quadrant 4 solution, which is where we actually are. So negative 0.986, which means our vector can be represented as 6.26, comma, negative 0.986 degrees. Another way to represent that would be 359.014, if you want to have it from the positive direction. All right, so the unit vector doesn't just apply to x and y directions. The unit vector of any vector u in the direction of u, denoted by what we say u hat, is given by u divided by its magnitude. So we have u that's a certain length, we divide it by that length, that scales it back to 1. So it's like multiplying by a scale factor of 1 over its magnitude. So if we have the vector u here and we want to find the unit vector, we already know what the magnitude of this is from earlier. It's 3 root 5. So u hat is going to be u divided by the magnitude of u, which is equal to 1 over 3 root 5 times 6i plus 3j, which gives us 2 on root 5 I plus 1 on root 5 j. Okay, it's asking us to confirm that the vector has a magnitude of 1, so that's pretty simple. We just apply Pythag to it, and we're going to find that the square root of 2 on root 5 squared plus 1 on root 5 squared is going to be the square root of 4/5 plus 1/5. 4/5 plus 1/5 is 1. Square root of 1 is 1. The vector describing the location of A relative to B, written as A, B, is easily found using vector addition. So if I were to go from, A relative to B, that should be B to A, is easily found using vector addition. So if we want to get from B to A, we have to go negative the direction of B, positive the direction of A. So this is going to be A take B. Similarly, the vector describing the location of B relative to A, which is AB, is going to be, I think I've jumped the gun here. So rather than describing it as A and B, we haven't done that yet. Let's describe it as the using the point O. So we're given this point O over here. So B to A is the same as B to O plus O to A. Right, another way we could represent that is negative OB plus OA. So similarly, the vector of B to A, AB, is going to be, well, if we're going from A to B, we're going A to O plus O to B, which is the same as negative OA plus OB. So if A and B are points defined by position vectors A and B respectively, then B to A is going to equal, negative O to B is negative B, and then we're going to add on A there. So we can see that B plus B to A is another way to write the vector A. So that's just adding the vector B to both sides. So example 10, determine the position vector locating the point B from point A. Calculate the length of this vector. So we're looking for AB, and then we want to find its length. So AB is given by negative O to A plus O to B, which in our case here, negative O to A is negative 2I minus 5J, and we're adding 3I, minus 3J. So if we compute this, negative 2 plus 3 is I, negative 5 minus J is negative 8J, and that is going to be the position vector A to B. So the length of this vector is just given by the magnitude of AB, which is square root of 1 squared plus 8 squared. Oh, sorry, negative 8 squared, but that's the same as 8 squared, which gives us negative root 65, which we can leave as that. There's no way to simplify it. Alternatively, in decimal form, that's going to be 8.06. All right, so that covers everything for 2.3. Thank you very much.